To calculate the amperage in a three-phase system using transformers, we employ a specific formula. This formula accounts for the apparent power, voltage, and power factor. The formula for calculating amps in a three-phase system is amps equals quantity 3 times kilovolt amps times 1000, divided by the square root of 3 times volts times the power factor. In this formula, kilovolt amps represents the apparent power in kilovolt amps. Volts is the line voltage in volts. Power factor is the ratio of real power to apparent power, often assumed to be 1 for simplicity, representing a unity power factor. Now, let's apply this formula to a scenario with 3 transformers, each rated at 500 kilovolt amps, connected to a 480 volts secondary. We'll assume a power factor of 1. Given the number of transformers is 3, kilovolt amps per transformer is 500 kilovolt amps, the secondary voltage is 480 volts, and the power factor is assumed to be 1. We can plug these values into our formula. Amps equals quantity 3 times 500 kilovolt amps times 1000, divided by the square root of 3 times 480 volts times 1. This simplifies to amps equals quantity 3 times 500 times 1000, divided by 1.73 times 480. Further calculation yields amps equals 1,500,000 divided by 830.4, which results in approximately 1806.36 amps. Therefore, each phase in this system will carry approximately 1806.36 amps. It's crucial to consider this calculated current when selecting appropriate conductors, circuit breakers, and other electrical components to ensure safe and reliable operation of the three-phase system. Always consult relevant electrical codes and standards for specific requirements and guidelines. The calculation relies on accurate input values, particularly the kilovolt amps rating of the transformers and the line voltage of the secondary. Ensure these values are correctly identified from the transformer nameplates and system specifications. The power factor assumption of 1 simplifies the calculation. However, in real-world scenarios, the power factor may be less than 1, indicating a reactive load component. If the actual power factor is known, it should be used in the calculation for a more accurate result. For example, if the power factor is 0.8, the formula would be amps equals quantity 3 times 500 kilovolt amps times 1000 divided by the square root of 3 times 480 volts times 0.8, which would result in a higher amperage value. Understanding the impact of power factor on current calculations is essential for efficient and safe electrical system design. The calculated current represents the expected current under full load conditions. It's important to account for potential overload conditions and include appropriate safety factors when selecting electrical equipment. Overloading transformers can lead to overheating, reduced lifespan, and potential failure. Therefore, it's recommended to design the system with sufficient capacity to handle anticipated load variations and future expansion. In practical applications, the transformer impedance also plays a role in determining the actual fault current. Transformer impedance limits the current during short-circuit conditions, protecting the transformer and connected equipment from damage. The impedance is typically expressed as a percentage of the transformer's kilovolt amps rating. When performing short-circuit studies, the transformer impedance must be considered to accurately determine the available fault current at the secondary terminals. The calculated amperage value of 1806.36 amps represents the line current in the three-phase system. The phase current, which is the current flowing through each winding of the transformer, may be different depending on the transformer connection type, such as delta or Y. For a delta-connected secondary, the phase current is equal to the line current divided by the square root of 3. For a Y-connected secondary, the phase current is equal to the line current. Understanding the relationship between line current and phase current is important for proper transformer protection and coordination. The transformer kilovolt amps rating indicates the apparent power that the transformer can deliver without exceeding its temperature limits. Exceeding the kilovolt amps rating can lead to overheating and damage to the transformer insulation. It's important to monitor the transformer loading and ensure that it remains within the specified limits. Various factors can affect the transformer loading, including the connected load, voltage variations, and ambient temperature. Proper cooling and ventilation are essential to maintain the transformer within its operating temperature range. The voltage rating of the transformer indicates the maximum voltage that the transformer windings can withstand without insulation breakdown. Exceeding the voltage rating can lead to insulation failure and short circuits. It's important to ensure that the applied voltage remains within the specified limits. Voltage variations can occur due to system disturbances, load changes, or voltage regulation issues. Voltage regulating devices, such as automatic tap changers, can be used to maintain the voltage within acceptable limits. The transformer connection type, such as delta-delta, delta-Y, Y-delta, or Y-Y, affects the voltage and current relationships in the three-phase system. Each connection type has its own advantages and disadvantages depending on the application requirements. Delta connections provide a stable voltage supply, while Y connections provide a neutral point for grounding. The selection of the appropriate transformer connection type depends on the specific system configuration and load characteristics. The transformer impedance also affects the voltage regulation of the system. Higher impedance transformers have better voltage regulation, meaning that the voltage drop from no load to full load is smaller. Lower impedance transformers have higher fault current levels. The selection of the appropriate transformer impedance involves the trade-off between voltage regulation and fault current levels. Transformer protection devices, such as fuses, circuit breakers, and relays, are used to protect the transformer from overcurrent, overvoltage, and other abnormal conditions. These devices are designed to trip and isolate the transformer from the system in the event of a fault, preventing damage to the transformer and connected equipment. Proper coordination of transformer protection devices is essential to ensure that the devices operate selectively and minimize the extent of the outage. Transformer maintenance is essential to ensure the reliable operation of the transformer over its lifespan. Regular maintenance activities include visual inspections, oil sampling, insulation testing, and tap changer maintenance. These activities help to identify potential problems early on and prevent costly failures. Transformer oil is used to insulate and cool the transformer windings. The oil should be tested regularly to ensure that it meets the required specifications. Contaminated or degraded oil can lead to insulation breakdown and transformer failure. Insulation testing is used to assess the condition of the transformer insulation. The insulation resistance and polarization index are indicators of the insulation quality. Low insulation resistance or low polarization index may indicate insulation degradation. Tap changer maintenance is required to ensure that the tap changer operates smoothly and reliably. The tap changer contact should be inspected and cleaned regularly. The transformer bushings are used to connect the transformer windings to the external conductors. The bushings should be inspected regularly for cracks, damage, or contamination. Damaged or contaminated bushings can lead to insulation failure and flashover. The transformer cooling system is used to dissipate heat generated by the transformer windings. The cooling system may consist of fans, radiators, or oil pumps. The cooling system should be inspected regularly to ensure that it is operating properly. The transformer nameplate provides important information about the transformer, including its kilovolt-amps rating, voltage rating, impedance, connection type, and serial number. The nameplate should be consulted when performing calculations, selecting protection devices, or ordering spare parts. Transformer standards such as Institute of Electrical and Electronics Engineers Standard C57.12.0 provide guidelines for the design, testing, and operation of transformers. These standards should be consulted when working with transformers. The National Electrical Code, also known as NEC, provides requirements for the installation of transformers. The National Electrical Code covers topics such as transformer overcurrent protection, grounding, and clearances. The ampacity of conductors connected to the transformer is determined by the transformer's rated current and the conductor's temperature rating. National Electrical Code Table 310.16 provides ampacity ratings for various conductor types and sizes. The overcurrent protection for the transformer is typically provided by a circuit breaker or fuses. The overcurrent protection device should be sized to protect the transformer from overload and short circuit conditions. The grounding of the transformer is essential for safety and to prevent voltage surges. The transformer should be grounded in accordance with the National Electrical Code requirements. The location of the transformer should be chosen to provide adequate ventilation and access for maintenance. The transformer should be protected from physical damage and environmental hazards. The installation of the transformer should be performed by qualified personnel in accordance with all applicable codes and standards. The operation of the transformer should be monitored regularly to ensure that it is operating within its design limits. Any abnormal conditions should be investigated and corrected promptly. The maintenance of the transformer should be performed on a regular basis in accordance with the manufacturer's recommendations. The disposal of the transformer should be performed in accordance with all applicable environmental regulations. When calculating the amperage for a three-phase system with transformers, it's crucial to adhere to safety precautions and guidelines. Always de-energize the equipment before working on it. Use appropriate personal protective equipment such as gloves, safety glasses, and arc flash suits. Follow lockout tagout procedures to prevent accidental energization of the equipment. Be aware of potential hazards such as high voltage, arc flash, and confined spaces. Seek assistance from qualified personnel when necessary. The accuracy of the calculation depends on the accuracy of the input values. Ensure that the kilovolt amps rating, voltage rating, and power factor are correctly identified. Use appropriate units for all values. Double-check the calculations to avoid errors. Consider the impact of harmonics on the current calculation. Harmonics are non-sinusoidal currents that can increase the root mean square current in the system. If harmonics are present, the current calculation should be adjusted to account for their effect. Consult with a qualified engineer to perform a harmonic analysis and determine the appropriate directing factors. The calculated amperage value represents the expected current under normal operating conditions. However, the actual current may vary depending on the load characteristics and system conditions. Use a clamp on ammeter to measure the actual current and verify the calculations. Compare the measured current to the calculated current and investigate any significant discrepancies. The calculated amperage value can be used to select appropriate electrical equipment, such as conductors, circuit breakers, transformers, and generators. Ensure that the equipment is rated to handle the calculated current. Consider the directing factors for ambient temperature, altitude, and conductor bundling. Select equipment that meets or exceeds the applicable standards and codes. The calculated amperage value can also be used to assess the capacity of the existing electrical system. Determine if the existing equipment can handle the additional load. Identify any bottlenecks or limitations in the system. Upgrade the system as needed to accommodate the increased load. The calculated amperage value is an important parameter for electrical system design and analysis. Use this information to ensure the safe and reliable operation of the electrical system. Consult with a qualified engineer for assistance with complex calculations of system design issues. Remember that electrical systems can be dangerous. Always exercise caution and follow safety procedures when working with electrical equipment. Obtain proper training and certification before performing electrical work. Comply with all applicable codes and regulations. When calculating the amperage for a three-phase system, consider the source impedance, which affects the available fault current. A lower source impedance results in a higher fault current, which can impact the selection of overcurrent protection devices. Also consider voltage drop, which can affect the performance of equipment. A higher current can lead to a greater voltage drop, potentially causing equipment to malfunction or operate inefficiently. Account for motor starting currents. Motors draw a significantly higher current during startup and during normal operation. The overcurrent protection devices must be able to handle the motor starting current without tripping. Consider the impact of power factor correction capacitors. Power factor correction capacitors can reduce the current drawn from the source, improving system efficiency and reducing voltage drop. However, capacitors can also introduce harmonics into the system. Account for the diversity factor of the load. The diversity factor is the ratio of the maximum demand of a group of loads to the sum of the individual maximum demands. The diversity factor can be used to reduce the calculated amperage for the system. Consider the future load growth. The electrical system should be designed to accommodate future load growth. The calculated amperage should be based on the anticipated future load, not just the current load. Perform regular load studies to monitor the system loading and identify any potential problems. Use power monitoring equipment to measure the current, voltage, power factor, and other parameters of the electrical system. Analyze the data to identify areas for improvement and optimize system performance. Consider the use of energy-efficient equipment. Energy-efficient equipment can reduce the current drawn from the source, saving energy and reducing operating costs. Implement energy management strategies to further reduce energy consumption. Educate employees about energy conservation and encourage them to adopt energy-saving habits. By carefully considering all of these factors, you can accurately calculate the amperage for a three-phase system and ensure the safe and efficient operation of the electrical system. Always prioritize safety and consult with qualified professionals when necessary.